Okay, so I'm gonna come up here and adjust my rheostat till I get 1.65 volts across 33 the 33K. So I'm thinking I'm gonna stop right there. 1.66, that's close enough, right? Now what do I need to do? I want to set the voltage collector to emitter to uh, 2 volts, right? I got my leads backwards, but that's no big deal. So I'm gonna come up here and adjust this so this gets to 2 volts. Okay, that's pretty good. And what do I need to do? Okay, I'm gonna measure across resistor 2. I'm gonna measure across RC. And we're measuring 760 760 millivolts. So VR2, and then we're going to use that to compute IC. So what's that? That's a can take 760 and divide it by 100 and come up with 50. All right. Somebody say 50. So what we got? What's our collector current? What would that be? Most of these you should be able to do this in the head. If I divide by 100, what would I do with this? I'd move the decimal point to the left 2 times. 7.6 microamps. So we can do that in our head. All we got to do is just move the decimal point over twice, right, in your head. Or just move the decimal point. Yeah, if we move it over twice, just move it right there and call it 7.6 microamps, right? Are we okay? Huh? Milli. I'm sorry. Are we okay? We okay? Okay, so now what do we need to do? Okay, so we'll adjust it to 4 volts. So I'm going to go over and put it right here. Collector to emitter. And we're going to adjust it to 4 volts. That's good. It's going to range on 4 volts, but this looks real good, right? Then I'm going to go across the resistor again. Oh, I don't know why I'm doing that. Okay. 777 or 7.7 millivolts, right? Yes? Okay. All we have to do is just put the decimal between the two and call it milli. Are we okay? And what do we need to do next? Okay, so we'll go up to 6 volts. My meter's going to range. Oops. Okay, so 6 volts, right? And let me go back now. 790 or 7.9, 7 point or 8 millivolts. Around 8 millivolts, right? Okay. Everybody okay? And then what next? Okay, whoo, that's 8 volts. Uh, 8.2, 8.2 millivolts. So notice the current, collector current stayed fairly constant, even though we changed the collector voltage. Wasn't that neat? Are we okay? But if we use this to calculate beta, we notice that beta wasn't constant, because if it was constant, then that voltage across the collector, would have stayed the current flow in the collector would have stayed exactly the same. So what was the minimum beta we had? Well, that would be when we what was our minimum voltage? Huh? 7.2. And their maximum voltage is 8.2 millivolts. 8.2 milliamps. So beta varies. It's not varying very much, right? But if I came up here and changed the temperature of the thing, can y'all see what's happening? All I'm doing is what? Touching it with my 98.6 degree finger. So that's why we really can't we try to stay away from beta, because why? Well, not only temperature, because it even changes with current. It changes a little bit with collector current. Not much. And then, of course, the other problem is it changes with temperature, right? Okay, so what do we do now? We're going to come over here and reset our base current. So what do I need to set the base current? Okay, what voltage do we need? What? 3 volts? 3.3? Huh? Did we use 8 volts? Oh, I didn't know this. Okay, let me go back and do 8. Let's go back to 1.65. No, I don't. I have my glasses on my head, and I don't have a lab in front of me. Okay, 1.65. Let's go back and do 8. I'm sorry. I thought that is 8. That was 8, right? We did do 8. We do 8, Mitch. What was the 6, guys? 8.2. Yeah, but notice if beta was we didn't change the base current. So if beta was constant, that means that resistor would have dropped the same voltage through all those things. But it didn't, but it stayed almost the same. And that's that little tiny slant that we looked at that's caused by the actual internal resistance of the transistor. Okay, so let me go back to our 33K, and we need to set this for what voltage now? Good enough, right? Don't say. Okay, we're going to go back to our collector emitter and start the whole thing over again. So we're going to drop this back down to 2 volts again, right? 2 volts the first one. Okay. 2 volts collector to emitter. And this is the voltage drop across our resistor. So we're going up about 10 milliamps, right? So what would that be? About 15 milliamps. We're still doing the same thing, just move the decimal point over, right? You understand, and call it milli. Are we okay? Yes? Okay, so we're going to come over here and go to what voltage next? Okay. We okay? Okay, this is the voltage drop across the resistor. 15.2 milliamps, right? Are we okay? Now notice base current went up and collector current went up, but still it's steady. It's going to rise just a little bit because there's a little slant to it. Are we okay? Everybody okay? 15.3 milliamps. What's our next collector current? I mean collector voltage. Collector to emitter voltage. Okay, so it's 6. 15.7. Are we okay? Everybody okay? Millivolts. Yeah. No, we got 1.58 volts. Okay, so here's the voltage. 1.58 volts, which would be what? 15.6 milliamps. Or 15.8, sorry. My little crutch is slipping there. I need to tape it down. We okay, Mitchell? Okay. So we're going to go up to 8. That's a pretty good one. And here's the voltage across there, 1.62 volts. So that'd be 16.3 milliamps. I see. Are we okay? So notice base current goes up, collector current goes up. And then we can vary collector to emitter voltage. So that's what the amplifier is doing. When it amplifies, the voltage collector to emitter is changing, but beta stays not perfect, but relatively, we can't say it's constant because it does vary. Okay, guys, what do we need to do now? Okay, so what voltage do we need across our resistor? 4.95. We did really good on that, guys. Okay, that's the best I can do. All right, we ready? Then we're going to go back to the resistor and do it. Oh, I'm sorry. Collector to emitter first. And then we'll drop it back down to 2 volts. Okay, that's 2 votes. We're okay? No, this is voltage collector to emitter. This is not, okay, voltage collector emitter is given, right, Mitchell? Okay, so here's the voltage drop across the collector resistor. We should expect it to be bigger because the base current went up, right? Two point 2.19. We need to carry this out, you know, because these guys don't vary that much, right? 2.18 should give us 21.8 millivolts, right? I'm sorry, 21.8 milliamps. We okay? We okay? You okay, Mitchell? On 2 votes. No, 2.18. Right. Which would give us 21.8 milliamps, right? Are we okay? Okay, here's voltage collector to emitter. We want to go up to 4. That's close enough, right? Well, did go to 4. Here's voltage drop across, I guess, R2, 2.27 volts, 22.7 milliamps, right? Are we okay? Ready? Okay, then we'll go up to 6 volts. That's good enough. 2.37 volts. I mean 2.38. Which would be 23.8 milliamps, right? Change the sign. Are we okay? Okay, and then what's the last one? Hey. That's good enough. .48 or 2.49. It just changed on 2.48. So 24.8 milliamps or 24.9 doesn't make any difference. Change to 24.5. Now, what's making it change, y'all think? What temperature? Yeah. Yeah, might be. Yeah, but we're getting a lot more collector current. We're pushing your dynamic personality, your static personality, your electric personality. But say we're getting this, it's affecting it now more than it did before because we're getting a lot more collector current, right? And the transistor's dropping voltage. If the transistor's dropping voltage, then P is equal to V times I. So the collector current is actually causing the transistor to warm up a little bit, right? That makes sense? Probably constantly, yeah. Change. Okay, so what do we do next? Plot the chart. So what is the maximum IC we have? The maximum IC we ever had. What was the maximum IC we had? 28, 24.8, 24.9. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 divisions. That's very strange. Usually they end on a 5 or a 10. And what was the maximum we had? 25. Well, 25. We'll have to go to an even number, right? And we'll have to round up. And we have 17 divisions. So it looks like the best thing to do, guys, is probably make them worth about 1.5. Let's do it. Let's make it a little easier. Just go ahead and make it like 2 milliamps per division. What was the lowest we had? No, the lowest. 7.6. That'd be good. So let's make each one of them 2 milliamps apiece. Y'all know what I'm talking about. IC's where? On the left. Then what's across the bottom? Voltage collector to emitter. Y'all know how to do the graph, right? So what we're going to make each on the vertical axis, what are we going to make that? 2 milliamps per division. Now, what you're expecting to see is you'll have to do this one. When we started, we were already up in this line up in here. Y'all understand that? And so we didn't get it down. We could have done that, but we didn't get it down. Sorry. So we didn't get it down to 0. We never had a base current of 0. We could have done it with our pot, and then you could have come over here and grafted it up right here. So basically what you'll do, you'll start from 0 and then come up to your first dot. Does that make sense? And then when you do your other dots and connect them together, you're going to end up with a slight upward slope. It's not going to be much. Now, once the transistor gets turned on, when the transistor turns on, it was perfect. This would be a what? That would be a straight line. But we could go outside and we would get different measurements. I could touch it and we could get different measurements, right? You understand? We could turn off the air conditioner and we could get different measurements because beta varies with what? With temperature. But the beta, so let's calculate the beta for each one of these two. So it's going to be IC over IB. And you'll see the beta is fairly constant, but it's not constant. Dang it.
Like that.
Yeah. It's going to slide up a little bit.
So 7.6.
Yeah. So 2 volts, 7.6 milliamps. So all of you want, right. Well, you're supposed to do your other you're supposed to do your other voltages. 2, 4, yeah. Supposed to do your other voltages. 2, 4, 6, 8. That's its current, right? I'm saying. And then we'll go into the next line, and we'll do 2, 4, 6, 8 in the base current here. And what you're supposed to do, guys, is you're supposed to write the base current on the line. You'll see what I did? Yes or no? So that's the way you do what we call the collector characteristics curves. So over here, and we're going to do it for how many voltages? 2, 4, 6, and 8. So 4 voltages. And how many currents? 4 currents, right? You understand that? And then we'll end up, and then you get a straight edge, and you connect that together. It should have a slight upward. It should have a slight upward slant, right? So we're not going to do the collector currents. Y'all can do those. So what beta did we have at 50 microamps with the voltage collector to emitter of 2 volts? So how do we calculate beta? Beta is equal to IC over IB, right? So I gave y'all the IBs, but we had to record the IC. So what beta do we have right here? So what was our first IB? 50 microamps, 2 volts. So that would be what? 7.6 milli. Is that right? Yes or no? Okay, then I would divide that by 50 micro. And what do we get with our first beta? What's that? That has no unit. Beta has no units. It's a multiplier. I hope not. So you got 7.6 milli divided by 50 micro. What's that? 66? I don't know how. 152? We're taking IC and we're dividing it by IB. Here's my IBs up here. 7.6 milli divided by 50 micro. Yeah, that could cause a big problem. 152. Is it between 30 and 300? Yes. Huh? No, Mitchell was doing it backwards, so I was trying to get him to see that. What's our second base current right here for 4 volts? Okay, so this is what you say, 154. What would it be for 6? Have y'all done that yet? So see why we don't use beta, Barry? Because it does what? Yeah, it changes. So this would be our worst case. Let's go all the way up to here, 8 volts at 150 microamps. So what was our collector current up here? The last one we did, 24.9 or 25 divided by 150. This is milli divided by 150 micro. So what beta did we get right down here? About that much. What's that? 166. So see, even in our circuit, beta varied between what? 152 all the way up to what? 166. So that's why we don't use beta. Now it's close, right? You understand? But look, when we look at the data sheet, what does it tell us? Well, the data sheet tells us it could be anywhere between what? 30 and 300. Is 152 and 166 between 30 and 300? Yes. Right slab in the middle. Pretty close. So normally for a 3904, we use a typical beta of 100. So that's basically what we do. We basically choose one closest to the center. And you'll see it works. It's not perfect, but it's okay for approximations, right? Y'all want, huh? Because I'm not going to sit down and wire up a circuit to get the beta of this transistor when I could pop this out and put another 3904 and it would come up with different measurements when I can look at a data sheet and choose one in the middle between the minimum and the maximum. You're right here. This transistor would have operating at this range, at this temperature, this transistor would have a beta here. Well, we could come in here tomorrow and hook up this same circuit. If it's not the same temperature in his, we'd have a different beta. Odds are it's going to be close to this, but it would be different. But from the data sheets, not from measurement. So that means every 3904 is going to have a typical beta of about 100. Is that true? Well, it's close enough for approximations, right? So I can figure it. So beta, anytime we use beta, we're definitely using what we call an approximation. Yeah, there's a tolerance between 30 and 300. Is that a pretty good tolerance? No, it's between 30 and 300. I mean, it's just, and every one of them would have a different rating depending on the transistor. So yeah, but the problem is it's a big tolerance. So what do? Well, we choose something kind of in the middle, and don't round. So 100, what we use for a 3904 and a 3906. By the way, 3904s and 3906s are what we call complement transistors. You know what that means? It means they have exactly the same ratings. It's just that one of them's TNT and one of them's NPN. So later on when we look at how we actually get some real power out of these transistors, we'll run with what they call complementary pairs. So like a TIP41 and a TIP42. The TIP41 is an NPN, and the TIP42 is a PNP. But they have the same what? They have the same electrical characteristics. So that's why we use beta. It's pretty constant, but like I said, we could hook up the same circuit. All I know, it'll probably be around 100. So we got a pretty good beta out of this guy. But I could change it with what? Temperature, right? Unless we do something to compensate for that. So what do we call these curves? We call these collector characteristic curves. That's what they're called. Very seldom do they give these in data sheets. Most people use beta, and they'll come up here and just draw a straight line. And then they use those. Because we know it's at a slight slant, but it's at a slight slant, right? So even if we use a typical beta, it's not going to be perfect, but it's going to be close enough for what we call government work, right? So y'all going to do those charts and answer y'all's questions, right? What's y'all's next lab after 35? Or 33. We're working on 33, I'm sorry. No, what's the title of it? I'm sorry. I know 34 comes after 33, but what's the title of 34? Comedy Emitter. Okay, so let's go ahead and start that one, and then we'll finish this up next class. So we've already covered the common emitter amplifier, so I need a 3904. What size resistors do I need? I don't know. In the OLAB book, it's a what? Let me look. So we're looking at the circuit, not at the. So what I'm gonna do on page, I'm looking at figure, or I guess on your book it would be 34-3. This is the first circuit we're going to construct. Is that the common emitter? Right? Let me see, Bob. No, that's not the circuit we're building. Maybe, no. No, we're not building this one. We're building, not that one. That don't give us any value. Turn the page. No, we're building this one. Okay. 34-3. Now, we're going to have to make some modifications to the circuit. See if y'all can help me out. First of all, what we're trying to do, they're using a fixed voltage divider connected across an AC source. And then we're bringing that into a capacitor. What's the function of the capacitor? Oh, this lab is not due till next class, guys. Y'all don't have to turn it in now. Y'all hear me? So this is a polarized capacitor. And why do we need that capacitor right there? Coupling, but what it does is it keeps the DC bias right there, right? It don't let the DC bias get out. So it lets us bring in this AC signal into the base, but it don't let the DC bias get out, right? So one of the functions of a capacitor is that it blocks DC, allows AC to pass, depending on the frequency, by the way, guys. And if y'all hadn't had AC, you'll learn that. We're going to start off by not putting the bypass capacitor in there just to figure this out. What's our VCC voltage? Okay. And then we're going to take the collector. We're going to come out through another resistor, polarized with the positive on that side. Because we're going to have AC on this side, DC on that side, right? And then we're going to hook this up to a load resistor. What size load resistor? And they're calling this RL. And we're calling this RC. This is, by the way, generically, this is the way we label these transistors. We call the collector resistor RC. We call the emitter resistor RE. And then, yeah, this right here would be R1 and this would be R2. Now, this is generic, right? In real life, this could be R53, that could be R74, or it could be, right? This is just generically when we set these things up. What do you mean? Yeah, because here they're using the generic numbers for an amplifier. These are generic. So normally when we draw these things and we don't want to assign numbers, we call this resistor right here R1, we call this resistor right here R2, we call the collector resistor RC, we call, okay. So that's why those get R1, R2, that's why those get R1 and R2. No, generically, when we talk about amplifiers, instead of me making up R numbers, generically, when I get into real life, this right here might be R15, this right here might be R32. It depends on how they're located on the board. Normally, when they start numbering resistors on a circuit board, normally, not always, they usually start in the upper left-hand corner, they go across the top, and then they move down the board from left to right. Now that's not rules either. That's just normal. But when we start drawing the transistor amplifiers to make us be able to put formulas, right? You understand? So if I put a formula, if this is R53 and that's R65, then I cannot put anything on a formula sheet. But if I always call that R1, I always call that R2, and I always call that RC, and I always call that RE, and then you apply it to the circuit that you're in, then these formula sheets make some sense, right? So now if this is always R1 and always R2, I can say, okay, if I need to calculate the voltage drop across that resistor, I don't worry about what it's going to actually be in the circuit. I'll just say R2 over R1 plus R2, right? So that answers your question. So since they've used R1 and R2, what did they do right here? Call these two what? Which we're not going to use because we got a big problem. Now the problem we have is that I need 10 millivolts peak to peak right here. Yeah. It's over there somewhere. It's going to set that to 10 millivolts. Over there on 38-3. I'm sorry, not 38-. You're on your book. It's 34-3. In that table. So look at the first, the voltage we're looking at. We're looking at 10 millivolts. Okay, y'all understand. But that means if I set this right here to 1 volt, and then the ratio of these two resistors, so I could calculate so my voltage is across R4. So let's use the voltage divider formula. So VR4 would be equal to what's R3? I mean, what's R2? What's R4? Huh? 100 ohms divided by RT. What's the sum of those two resistors? 10.1 K. Okay, and then I'm going to multiply that times 1, which is what they're looking for. And then what voltage does that give me? Should be pretty close to 10 millivolts. It's not going to be exact. Huh? Okay, 9.9 millivolts. The problem is my function generator does not go down to 1 volt. So these are fixed equal to 1 volt. I will not get 10 millivolts over there. So I need some voltage divider that gives me the ability to set 10 millivolts. So what are we going to change this to? A pot. What can I do with a pot? I can get any voltage I want to. I set the ratio of the resistors, right? Y'all understand that? So we're going to go up there. Y'all need to modify your print. I'm going to take this out right here. And I'm going to change this to a 10K pot. Huh? Yeah, probably every circuit that, this is the only circuit we'll hook up in this lab. So now what can I do? I can come up here and set this to whatever voltage I want, like 5 volts or something like that, and then I can adjust it so I get 10 millivolts in. Or I can set it to 2 volts or whatever I want, right? Y'all understand that? 2 volts would probably be easier. So we're going to modify our circuit. So we're going to redo this and put a what right there? A pot, 10K pot, and we're going to call it R3. So I just so happen to have a 10K pot up here. I think it's 10K. It might be 1. The size of the pot don't make any difference, right? You understand that? It just depends on how much power it would produce. So let's see what I got. That don't make any difference. Okay, so what do I need for R1? Okay, 47K. What do I need for R2? A 10K. What do I need for RL? I mean RC. Let me erase this. What? What do we need for RE? And we'll add the capacitor later. So let's see what we can do. So let's calculate what we should expect for VB. VB is the voltage drop across R2. I mean that should be pretty easy. What formulas are we going to use? Where did you learn these formulas at? They say hopefully you learned them, but you want credit for it. So I use the voltage divider formula because you don't have to calculate current, and most of this stuff you can kind of do in your head. So VB would be equal to 10K divided by 57K. I'm going to leave the K off because they're going to do what? They're going to cancel, and then I'll multiply that times 10 volts. So that gives me VB. Do that with one use of the calculator. If you try to calculate current, then it's going to take 2 formulas, right? You understand that. So this voltage divider formula is the neatest thing. So what do we get? What are we going to expect on VB once we get this thing hooked up? 1.75 volts. Let me erase that guy right there. Dang it. So VB is equal to 1.75 volts. Everybody okay? I must not be. For you it is. Okay. So what's VE going to be? Well, VE, we'll use Kirchhoff's law, right? So VE is going to be 1.75 minus 0.7. So VE should measure what? 1.05 volts. To common. Then we're going to calculate IE. IE would be equal to 1.05 volts divided by 2.2K. Have I lost anybody so far? We're just using what law? You know what? You learned these in DC, right? 477 microamps. Okay, now this is a series circuit. I don't know about the transistor, but by George, I know that IE and IC are close enough together we can use them as equal, even though they're not. So if you see on a test IC equals IE, then you're going to call that false, right? If you say IC is equal to approximately IE, then that would be true. Which is the highest current flow in the transistor? Of the 3 leads, which is the most? i.e., IC, or IB. IE is the highest, right? Because it contains both base current and collector current. Okay, now I could calculate VRC. So VRC would be equal to 477 micro times 6.8 K. .24 volts. Then I could calculate VC. VC would be equal to 10 volts minus 3.24 volts. 6.76. Is the transistor operating closer to cutoff, or is it operating closer to saturation? Operating closer to cutoff. The higher the voltage is, what would we like it to be? Well, we'd like it to be 5 volts. For an amplifier, we want it right in the center. Why can't we get it right in the center? Because we're using standard resistors. What's the odds of me finding 2 standard resistors that would put that right in the center, right? You understand? So all these resistors are standard resistors. The odds are we're going to operate this thing a little bit toward cutoff or a little bit toward saturation. So that means it's toward cutoff, which means it'll clip the tops before it clips the bottoms if we overdrive it. Voltage to collector to emitter, it gives you the formula. Voltage on the collector, 6.76, minus the voltage on the emitter, 1.05. So what's our voltage collector to emitter? Yeah, 5.7 volts. 5 point. Okay. What region are we operating in? Are we operating in the cutoff? Are we operating in saturation? Are we operating in the active region? How do you know that? More than 1 volt, less than VCC. So what we'll do is we'll go ahead. Next class I'll come in here. We'll flat the resistors and we'll wire that. We'll run it without the capacitor, bypass capacitor, and then we'll run it with the bypass capacitor. So what should be the gain? Y'all look at y'all's formula sheet. RE is not bypassed. So what would the formula be? AV, so A is gain, right? V means it's what? Voltage gain is equal to R out divided by RE. R out would be equal to 6.8 K. 6.8 K, Rich. In parallel with a 10 K. I didn't put the parallel formula. I hope y'all can get that. 6.8 K in parallel with 10 K, right? What's R out equal to? $6.8K. So the output resistance or impedance is set at that point right there. So the output current goes 2 different places, and that dot means that these 2 resistors are seen in parallel, right? So I would come over here. The AV we expect would be 4K divided by 2.2K. So what gain should we get right now? Not much, but we are going to get a gain. Not much, of course. Yeah, so we're going to get a very small gain, 1.8. Now that's a voltage gain. What unit is that? 1.8. What unit is that? Yeah, it don't have a unit. It's a gain, right? You understand that? Gains don't have units. For some reason, we pound on volts, amps, ohms, watts. Make sure you put the unit. Make sure you put the unit. Make sure you put the unit. So when we get to this point, people think there's got to be a unit on the game. Yeah, they want. Actually, G stands for conductance. So if you put a G out there, that would probably. G is total conductance. Okay, guys. Y'all have a good weekend. Some of y'all still see me though, right?